Welcome everybody, and thanks for being here. It's a lot of you attending. Thank you, and welcome to this webinar about challenging deepfakes, detecting AI-generated images with geometrical analysis and deep learning. So we have a lot of stuff to see, so let's jump into the topic. So just a couple of words about me. I am Marco Fontani. I am the forensics director at Amped Software. We'll tell you more about this company in the next slide. I am a computer engineer with a PhD in image and video authentication. So I've been working on this kind of topic since before deepfakes were something. And I've been a member of the IEEE Information Forensic and Security Technical Committee. So I know a lot of the professors working in this field, and they're having a lot of fun lately. And I also have experience as a forensic expert. So I've provided witness expert. I worked as a witness expert on some cases. Okay, and about the company, Amped Software is a company founded in 2008 in Italy, and it has a subsidiary in the US. And we make the main software for image and video forensics for law enforcement and government agencies in more than 100 countries. So that's our mission, to create the solution for this need. The vision of the company is justice through science. So whatever we do, whatever we put in our products, we do our best to keep it always correct and repeatable, accurate from a scientific point of view. This is a picture of the company, but it has grown since then. So we are more than this now. Just one more minute about the Amped ecosystem. So I just want to give you an idea of the kind of solutions that we've developed, and then we go into the topic, into today's topic. So the flagship product of the company is Amped 5, also known as the complete Swiss knife for image and video forensics. Okay, this is basically the interface. So you have a lot of filters, and you can load proprietary videos, surveillance videos. We have a powerful video conversion engine. You're then able to process the video, analyze in depth the metadata, the container, and you can enhance the image and the video. This is the main power. So you can reduce the blur, like you can see in this case. You can measure things, you can do a lot of stuff, and then you can create a forensic report which will document everything you did in a very repeatable way. Then it takes a bit of training to use this software because it's very powerful. So we created a different solution, which is conceived for non-experts, okay, but for frontline officers, and this is called Amp Replay. And as you can see from the drawing, it's a much simpler product, okay, a much more simple interface. So you can still convert the videos with the same conversion engine, because this is essential, of course, and then you can process them to some basic enhancements, powerful annotations, which you can also do in 5, of course, like zooming, reduction, and everything, and then exporting still in a forensically sound manner. Then we have DVR-Conv, which is only about converting videos. So we like to say that it will turn your spaghetti video into some flat video that everything can play. And so this has a very, very technical interface, I would say, and not very fancy, but powerful. And we also have a command line solution for this, which is called Amped Engine. We'll do basically the same thing, but via command line. And finally, and this is the product we will see most today, we have Amped Authenticate. You see a microscope here because this is the software that will let you investigate in deep images and videos to detect traces of manipulation, but also traces of their processing history. So you can understand whether an image was captured with a specific camera model or a specific camera exemplar, okay, with sensor noise analysis. So as you can see, we cover the entire workflow, okay, from first responders to technicians to analysts, and our main customers are in law enforcement and forensic laboratories worldwide. Okay, now let's go into the topic of today. So we will do a bit of slides and a bit of software, okay? I don't like presentations where you just show the software and click buttons randomly, so I want to give you some concepts before. So we will see what is a deepfake. We will have a very simplified definition of it. And to say what a deepfake is, we have to talk a bit about AI and neural networks and the role of AI in deepfake generation, okay? Then we will go to how we can combat deepfakes, okay? Possible approaches to deepfake detection, showing you, of course, some practical usage examples with Amped Authenticate. And then we will draw some final remarks. You are very welcome to ask questions with the Q&A section, but I will address them at the end, so I have a feeling of how much time I have left and how much time I can devote to every question. Perfect. So deepfakes and why they are becoming so famous. Basically because they were born as a research, okay, but they were soon weaponized, okay. The first application of it was, not surprisingly, non-consensual pornography, okay. So very early in the era of deepfake, you had these bots on some social media apps that would allow you to send a picture of a woman or a man, of course, and you could ask the software to undress the woman. Okay, and this has become much more powerful nowadays and much more dangerous. Then they've been used for misinformation campaigns, for tampering evidence, and also to address some national security issues. For example, at the beginning of the war in Ukraine, we had a video of President Zelensky asking his soldier to surrender. That was a deepfake. It was not very well made, so it was soon debunked, but that was a very important step, I would say, in the age of multimedia forensics. So what is a deepfake? Well, deepfake means that the image video is a fake, so it's not is no longer an accurate representation of the original data. For example, here the face has been clearly tampered with, okay? But this fake has been created with the use of a deep neural network, okay? So that's the meaning of the word. Now, what is a neural network? Artificial neural networks, finally, are quite old method of machine learning, okay? They are historical. They date back to 70 years ago, maybe, okay? And their name reveals that they are inspired to the biological brain, okay? Because, of course, our brain is much more complex than a digital neural network, but still the main idea is that we have many neurons connected, okay, that will do some very simple processing, each one, but once they are connected, many of them, they become powerful, okay? This is represented usually in this way in a neural network. So you would have an input layer, then a number of hidden layers, and then the output layers, okay? And as you can see, we have these lines connecting the nodes, which are the neurons, okay? And these W's are the secret in the end. So once you specify the architecture of a neural network, the rest of the job is trying to find the proper values to these weights that will tell each neuron how much the input from this other neuron must be relevant. And thanks to some mathematical algorithms, you can use data to learn, okay, the proper weights to solve the task that you wanted to solve. That's the idea. Deep networks are called like this because they don't have just one hidden layer, but they have many of them. And there are many different architectures, so ways by which these neurons are organized. Okay, perfect. Neural networks are a universal tool, meaning that, theoretically speaking, they are universal function approximators. So you can use neural networks to do a lot of stuff. And they have been used, indeed, to do a lot of stuff, from simple recognizing handwritten characters to do email spam filtering. They have found medical applications, they have found financial applications, and much more, okay? But now, for the sake of deepfakes, we are mainly interested in some kind of architectures, which are called generative models, okay? And we will touch briefly three concepts, just very briefly, okay, that are at the base of some of the most common deepfakes you will find out there. The first one is generative adversarial networks, also called as GANs. The second one is autoencoders, and the third one is diffusion models, okay? So generative adversarial networks, it's the kind of network used for many deepfakes, especially until a few years ago. They were the most used technique, okay? And they're made like this. They are made with two neural networks, a generator, which will create pixels from nothing, and a discriminator, which tries to distinguish real images from generated examples, okay? So the generator at the beginning will start from random pixels and create some random stuff. And we have a discriminator. Let's say we want to have a generator that creates nice faces. We train the discriminator with millions of real images, real faces, okay? And the task of the discriminator is to learn to distinguish a real image from what the generator did. Of course, at the beginning, the discriminator has a very simple life because it's comparing a real face against noise. So it will say, haha, no, this is fake. But then, of course, you put them in a loop, okay? And so the generator is given feedback from the discriminator, and it will slowly learn to improve until it will be able to fool the discriminator. At this point, you throw away the discriminator, you keep only the generator, and you have your face generator, okay? And that is the technique, of course, a bit more complex than this, but the process is completely data-driven. So basically, you have to provide many real images to train a good discriminator, okay? And this is the technique behind the famous "this person does not exist.com" service, for example. You go to this URL, and you will find images of faces, just that, just the image of a face. You refresh the page, you get another one. You refresh the page, you get another one. All those people that you see do not exist. So I can show these faces without any privacy issues because this person do not exist. They've been generated by this system, right? This is StyleGun 2 that is used for this service. And yes, until some time ago, you could find some weird artifacts. Like here, you can see that we have one earrings and not the other. And also the ear on the left, it's a bit weird. But this is an image from a few years ago. Nowadays, they're getting better and better. And there are many scientific studies showing that humans are no longer able to distinguish a deepfake image like this, deepfake face, from a real face. Okay, and that was one. Now we have autoencoders. This is a different network. They were born as a way to compress data using a neural network. So you give an input signal, could be an image or some text, okay? And you create an hidden layer somewhere, okay, which has a lower number of nodes. And then you create an output layer which has just the same number of nodes, think about them as pixels, as the input. So you have an input which has 5 pixels, okay, or 5,000 maybe, and the output which has the same 5,000 pixels, but in between, you are forcing the network to compress this information in a lower number of neurons, okay? So by training, the network must learn how to represent this input into this limited space, okay, but then be able to reconstruct an output which is very similar to the input. Clever trick, okay? And so this is, for example, an example with a face, okay? You can see the input image, the output image, the intermediate representation. As you can see, the reconstructed image is almost better than the original because it has been also denoised in the process. And so researchers found this very interesting idea. So we will use an autoencoder for a person. So I will train an autoencoder to compress and decompress faces of subject A. Okay, so he has his own personal autoencoder. Then I train another one for person B, but I share the weights of the encoders. So I am creating a general purpose face encoding, okay, encoder. It will learn to encode simultaneously all kinds of faces. But then the decoder is specific to each person, okay? So we have a common encoder, but specific decoders. And now guess what you do? You swap the decoder. So you take face A, you encode it, but then you decode it with the decoder of face B. And intuitively speaking, you can understand that this step will map the common traits of faces into the latent compressed face. And when we go back to add the details to make the expanded face, we add the details of person B. That's the trick, okay? Now you take this trick and you put it into a more complex pipeline where you have the original face, you detect the face, you extract some landmarks, you align the face to be always in the same orientation. Now you do this trick with the network to convert the face, and then you do some processing to align it back, and there you go. Okay, so thanks to this core technology and some intermediate steps, you're able to do this. And this is what's the basis of this video that I would like to share with you. This is a nice example.
How's your head?
Oh, good. Fine.
Oh, I've been so worried about you ever since you ran off the other night. Are you okay?
Oh, it's Hardy.
I'm sorry, I have to go.
Okay, and you can see it works very well, right? So we have Robert Downey Jr. here in place of Christopher Lloyd, and it's impressive. And this is already an old video, okay? So yes, that's the technology behind it, these autoencoders. Oops, sorry. And then we have the most recent discovery, which is diffusion models, okay? This is even more technical, I would say, so I simplified it in one single slide. This is very, very simplified, okay? But basically, diffusion models are based on a concept by which you have a two-stage process, once again. We have a forward process where you start from an image and you add more and more noise progressively, okay, until you have an image which is only noise. And then you train a neural network, okay, that learns how to detect the noise, to predict the noise from the image. So you train a network that you give it this image and you ask the network, can you tell me what is the noise in this image? And then for this step, for this step, for this step, and so you use this network to denoise the image, okay? So you do this reverse process, starting from something which is completely noise. And now the trick is that you will condition this reverse process with some text prompt, okay? So you embed the text into the same latent space and you use the text prompt to steer the denoising process, which can go anywhere basically, towards what you want to achieve. That's the basic idea behind diffusion models. And this is the technology which is at the basis of the most common services used to create deepfakes nowadays. For example, I could use DALL-E 3 through ChatGPT, right, to create a photorealistic image of a dog playing soccer wearing Fiorentina's official shirt, which is my favorite team, okay? And I get this one. You can see that we miss an N here from the shirt, but you can iteratively talk to DALL-E and say, please improve it by adding the N in the name of the team, and it will create this one, okay? And you see that since I cared about the text, not only it added the N here, but you also see now the team name here, okay? Which is quite impressive. You could use Midjourney, okay, which is available through Discord. It's a paid service, this one as well. And you can use the prompt on Discord to ask a picture of two boys playing in a park on a sunny day, photorealistic style, and you get this image here, which is also stunningly impressive. But you can do much, much better than this with more complex prompts. And then you have stable diffusion, and you have many more, okay? This one you can download and use on your computer, provided it's sufficiently powerful, okay? And you can ask with a text prompt, an image prompt, and so on and so forth. Like here, I asked a portrait picture of a young woman, red hair, lipstick, photorealistic, and I got this. But you can use more refined prompts to get much, much better results. Okay, so in these 20 minutes, we had a very, very quick tour about the existing techniques. These are just some, of course, some of them, behind the creation of deepfakes. And now we want to talk about how we can fight deepfakes. So how we can detect deepfakes nowadays. So let me start saying that this is not a solved problem. So I cannot give you today the final solution to this because there is no final solution. And if someone tells you that they have the final solution, they are probably lying to you, okay? So let's see which are the possible approaches. We can tackle this task with integrity analysis, with conventional multimedia forensic approaches, with deep learning, used to fight deep learning, with physical and behavioral methods, okay? There could be more, but I think these four categories catch most of the existing techniques. And now we will go through each one of these, okay, very briefly, and I will show you first some slides and then some applications in the software of how you can do this, okay? So let's start with integrity analysis. So when you do integrity analysis, usually the goal is to prove that the video or image is untouched since the time of creation, okay? So it is a camera original, camera native content. That's the idea. And you can do this mainly in two possible fashions with active approaches, which means that the camera will embed some trustable information inside the content so as to safeguard the integrity. Okay, so I have this, I take a picture, but the app that I use to create the picture will put a lot of information in it, like the timestamp and maybe my personal identification, and then it will encrypt it with some cryptography and store it in a digital envelope together with the image. So the image is protected. And so the receiver can go and open this envelope and check that everything is correct. Okay, this is quite an old idea, but they're trying to reuse it nowadays for protecting the images. Of course, the good part is that verification is very easy because you just need the software to check that everything is right. But the main issue is that users must use and trust a special media creation app, right? So it is easily found that you can break this kind of system, okay, by checking how these apps work and finding workarounds, basically. Passive approaches instead, they go and analyze the media container or metadata to check the compatibility against an acceptable recording device or to reveal suspicious metadata, okay? So you have an image and you compare its metadata against a database, and maybe you detect that the image seems to be compatible with an iPhone or with some other capturing device, okay? Of course, this is effective and very fast, but it relies largely on the availability of enormous, rapidly evolving databases because new devices are created every day. And of course, they also have an issue with recapturing. So if I have a fake image, I print it on a piece of paper, then I take my smartphone and I take a picture of this printed image, I will fool both these approaches, right? Because the picture that I take of the picture is perfectly fine because it's being created by my smartphone. So this is something to always keep in mind. Okay, so an important point here is that with integrity analysis approaches, you may understand that you should not trust the image because it doesn't seem like to be coming from a pristine device. Okay, so it's not a pristine image, but you will hardly know why you cannot trust. So what has been done to the image, not how it has been done. This is usually unclear, nor where. So whether something has been changed or the image is probably just being processed as a whole. Okay, so it's quite limited in this sense. And we can see maybe some example of metadata analysis. Okay, so I will switch now to Authenticate. Okay, just a moment. Okay, you should be seeing the software now. So this is Amped Authenticate interface. You can see that you can load an evidence image here. And if you want, you can compare it against a reference image if you have one, so you can see them side by side. And then you have a filters panel where we have many different categories of filters, okay, for checking the image integrity, authenticity, looking for forgeries, and so on and so forth. You see that we have a dedicated deepfake detection category. We will go into that shortly, okay? So let's start with metadata analysis. I prepared some examples here. So you remember the picture of the girl with red hair that I created with stable diffusion? Well, actually, if you go and check the EXIF metadata, okay, you can see that this method that I used kindly embeds the entire prompt, okay, into the image. And so you can see the entire prompt that I use, so portrait picture of a young woman, red hair, lipstick, and also the negative prompt. So avoid unnatural face, avoid artifacts in face, avoid weird anatomy, and all the parameters that were used to create the image and the model and everything. So of course, if you find this, you are quite confident that the image is being created with stable diffusion, right? But of course, there's an issue. If I just resave the image, I just resave the image to JPEG, I will drop all the metadata and nothing is left. Okay, so the image is still usually the same, okay, but the metadata has been removed. So just by resaving the image, I laundered the metadata. This will still suggest that the image is not a camera original image, right? Because a camera original image has usually some metadata, but it's not enough to prove that it's a fake, of course. And the same we can do with the dog. Okay, this one was created with DALL-E, and you can find indeed DALL-E in the metadata of the file, right? You can find OpenAI and a lot of information, okay? But still, if I send the image via WhatsApp, this is what happens, okay? So after sending the image via WhatsApp, you will only find the metadata that are used by WhatsApp, and you will lose all the original metadata. So I think this is something very important to take into account. Okay, let's go back to the slides. And now we talk about conventional multimedia forensic approaches. So you know that fake image and video detection is a studied problem since 20 years for digital images and videos. And fake pictures exist since the existence of photography. You can go and check. There is a nice book by Hani Farid, which is a very important researcher in this field. And he published a book about fakes in history, okay? Yeah, it's very nice. There are also a lot of information on a website. And so you could see that politicians back in the 18th century, okay, were used to have someone manipulating the pictures. The approach that the conventional image forensic approaches use is that each processing step in the creation of an image leaves some trace in the picture. So if we are simplifying here, but let's say this box is a digital camera. When you take a picture, a lot of steps happens in the camera. The image goes through some lenses and then an optical filter, and then this CFA pattern. We don't have time to explain what it is. Then we have the image and sensors, some interpolation inside, some in-camera processing possibly. Today, a lot of in-camera processing actually. And then compression, addition of metadata, and so on and so forth. And this is your camera original image, the original product of your device. Then you will often share it through some social media. Someone could download it, reshare it, maybe recompress it, and this is the final image, okay? And now you're given this, and you want to use mathematics to understand what happened in the past, okay? And there exist a lot of tools for doing this. I will show you some examples in Authenticate. The interesting part here is that these tools were developed before the existence of deepfakes, but still they can help sometimes with detecting deepfakes. I will show you a couple of examples. So here we have this image where we have a face that was swapped, okay? And we have this filter in Authentic, which is called JPEG Dimples Map. This is something that was discovered a few years ago, okay? Which is just a strange way of some devices that they use to save the image to JPEG. So when they save the image to the JPEG format, they do a mathematical operation in the process in a slightly different way compared to the standard, okay? And so this will create a kind of watermark in the image, an intentional watermark, okay? When you manipulate the image in whatever way, you are likely to destroy the watermark. And so this filter will look for the presence of this artifact throughout the entire image. And if it is detected everywhere but in some places, those places are suspicious. In this case, you see that the artifact is detected everywhere, but here, okay, where the face was manipulated indeed. So although the modification has been done with a more recent technique, the trick that we use to detect it still works. Okay? This is another example. Once again, a face swap, okay? And we have these two ladies. And in this case, we are using a different filter, which is called aligned double JPEG compression. So this one is based on the idea that if you start from a JPEG image, you change something and save again to JPEG, the original pixels are compressed twice because the image is compressed in blocks, okay? So the original blocks are compressed to JPEG twice, while those that you touched only see traces of the last compression. And so by modeling this in a statistical way, you can tell apart which blocks belonged to the original JPEG image, which are the green ones, and which block have been manipulated in whatever way. That's why even if you use a deepfake algorithm, this detection algorithm doesn't care because it's checking for artifacts in the original pixels, not in the manipulated ones. And indeed, you see, it finds with fine-grained resolution that the face has been tampered with. And then one more example of classical approaches is this one. Once again, you see two faces here. You can tell probably even by the naked eye that there's something wrong here, but this time we are using an algorithm that checks for the noise level in the image, okay? And this algorithm is telling you that the noise is more or less the same everywhere, but in two places, the shirt of this girl and the face. Now, the sweater, okay, here you can see it's completely white, so this could be somewhat justifiable, but the face, from a visual perspective, is just a normal face like the other girl's one, but the noise level is completely different, and this is very suspicious, okay? And you could put this together with other things you could find, like the fact that you have much stronger correlation between pixels in this face than the one in the left, to say that probably the face on the right has something wrong. So these are just three quick examples, okay, to show you that you can still use the good old classical approaches, of which Authenticate is very rich, okay, to process some kind of deepfakes. However, back to the slides. These canonical methods have some limitations, and the main limitation is that they also suffer from post-processing, okay? So if I take an image, I do this kind of tricks, and then I share it on Facebook or WhatsApp, this sharing not only will remove the metadata, but very often it will cause the image to be downscaled and recompressed. And so you can understand that if you're looking to pixel properties, okay, and you downscale the image and you compress it, losing information, then of course everything can get harder. So here you can see an example where we have this spliced image. This is the ground truth, so the black part is the one that was manipulated, okay? You can see here several canonical methods output that work very well, but once you recompress the image, okay, you see that some of the methods don't work anymore. And if you also resize it, a lot of them doesn't work, don't work anymore, okay? That's the idea. Okay, and so what we do, because we actually are interested in analyzing images that come from social media, right? And so we need to use to equip ourselves with more weapons, and this is why we implemented also in Authenticate deep learning methods to fight deep learning. So the idea here is that instead of extracting some handcrafted features, we try to learn the features directly from the data, okay? So we can either use deep learning, but work on suggested features, okay? So I will take the input image, I convert it to some domain, like I extract the noise, or I go to a Fourier transform domain or something like that, and then I train a neural network. But this is no longer the method that is used mostly today. The method mostly used today is this one. You just train a very deep neural network, which will also learn which are the features of the image that you wanted to focus on. That's the idea, okay? And this is what we have put in Authenticate for this, okay? So I can show you some more examples. We have put in this deepfake detection category two filters, one for detecting face gun deepfakes, so the one created, you remember, with the generative adversarial networks, and one method to detect deepfakes created by diffusion models. Could you train just one method to detect both? Yes, in principle you could, but we decided to keep them separate as of now because that favored our training approach, okay? So you have to use both of them, okay? So let's start from the face gun. So I downloaded this face from thispersondoesnotexist.com, okay? And this face gun deepfake filter will detect the face, analyze it with a deep neural network, and produce an output, okay? Now, you see we have an output confidence score, 0.91. What does that mean? That's just a score that the neural network has at the end, okay? So at the end, the neural network says, I believe this image is a generative adversarial network image with confidence 0.91. The maximum is 1, of course, okay? That does not mean that this image is 91% a gun. We cannot say the probability, really, by which an image is a gun. And if someone tells you the probability, they're probably wrong, okay? We can just tell you how much confident the network is. The network could be perfectly confident, 1.0, and still be wrong. And this is always the case when you use machine learning approaches, okay? Now, you may say, okay, this is very easy because actually you have even the name of the GAN system down at the right, okay? But even if I crop the image and share it through WhatsApp, possibly adding some nice thing here, you can see that the confidence decreases because pixels have been processed, okay? But still, it's detected, okay? So we tried to keep this method robust as we could. It has limitations for sure, but we try our best. And yeah, you can try with many images from this person does not exist, okay? And actually, it was found, I think still by Annie Farid, who works a lot on this, okay, that if you download many images from this kind of service, okay, you will notice I've created a montage here with 4 images, okay. Now, if you look at it in this way, okay, without the filter over it, do you notice something strange? If you look carefully, you will see that the eyes are always in the same position. So if we just add some annotations that you can do with the Authenticate, you can annotate the filters, you can add shapes, you can add whatever, text, you can zoom, okay? Here I just added some lines to show you that you can see that the eyes are always in the same position because this is a prerequisite of the network to work, okay? And so unless you crop or rotate the image, pictures taken from here will always have the eyes in this position. Does that mean that every picture with the eyes in this position is a fake? Of course not, but it's an interesting clue. Okay, that was about FaceGAN. Now let's look at diffusion models. So let's go back to the dog playing soccer. Okay, the diffusion model deepfake will produce you a table, an output table, which tells you the predicted class and some scores, okay? So we trained this neural network with images from Stable Diffusion, images from DALL-E, images from Midjourney, and also a load of real images, okay? And we trained the model to say whether the image belonged to one of these 3 diffusion models or to no diffusion model, okay? In this case, you see that the system with the yes, I said soccer on purpose. You can see that the score of DALL-E is quite high, 0.82, okay? And so the predicted class is DALL-E. This is just a convenient way of saying which one is the highest score, okay? And then this one went viral on Twitter, I think a few days ago, okay? And we tried it with the diffusion model deepfake, and also this one, despite with a lower score, so we tried this one slightly less, okay? But still, it's matched to DALL-E. Now, this filter could sometimes swap one method for the other, but it's usually quite reliable in telling whether it's AI or not. That's the idea. And also, if you look at this image, it's very nice, but if you zoom, you can see that the thumb is a bit strange. Let me enlarge it for you. You can see that you can hardly hold something with your hand like this, right? But still, it was nice to see. Okay, let me see. Oh yes, this one that I showed you before, created by, I don't remember what, I think it was Midjourney, okay? Yes, you see it gets matched to Midjourney with a very, very high confidence score, okay? Perfect, so these are 2 filters that we included in Authenticate in the last years to try to combat deepfakes. Are they perfect? No, they can still get it wrong, but they are an important tool. Okay, and then what we have, of course, which are the limitations of these methods? Where the lack of explainability or reduced explainability. You get a score, but you cannot explain why. And that's a shared concern for AI, okay? You get a result, but you can hardly justify that result. Of course, for forensic applications, this has very important implications. Then there is a strong dependence on the match between the training dataset and the test dataset. So you train your detector on a lot of images, you do your best, but then tomorrow a new system comes and it fools you. There's nothing you can do besides keep on training with more images. And for this reason, it's an arms race. So you create better detectors, but your detector will be used to train better system to create fakes, okay? Finally, we have physical and behavioral methods, okay? So this is a completely different approach, and the idea is to reveal inconsistent properties in the geometry of the image, or we will see later in the physiological behavior of people, okay? For example, one is shadows analysis, okay? So if you have an image, okay, where you have shadows, and these shadows are generated by a single pointwise light source like the sun or a spotlight, okay, you can do this kind of analysis. So this is the image, and you can draw some wedges to create these constraints, okay? So I click on a point, and then I click on a range of points that could be the responsible for this point on the shadow. I don't know exactly where on the horse ears I should click, so I click from here to here, okay? And intersecting all of them, you see that I get this yellow region, which is called the visible region, the intersection between all of these green triangles, okay? And this region must contain the light source, like in this case. This is an original picture, and you can see that the light source is indeed inside the yellow thing, okay? And, yes, okay. And you can do the same also for reflections. So if you have an image with flat mirrors like this, you can connect a point on the object to the range of points on the mirror, like this. And in this case, you don't have the light source, so you don't know. But this yellow region will go to the vanishing point of the mirror. So these wedges must intersect somewhere. Otherwise, there's something wrong. Okay? And now you can do this with Authenticate. So let's go back again to the image with the two boys in the park, okay? And we can do this analysis together maybe, okay? So I will just click on this point, and then I select the head of the guy. Let me show the constraint. Then I click on this point, and I select the head of the guy. I'm being very conservative, you see, so for sure. And you can already see here that, yes, you do have an intersection, okay? But the intersection is wrong because the sun is here, okay? It's not embedded in it's not contained in the yellow region. So although the system is feasible, you can tell that the image is, I mean, this will not tell you that it is a deepfake, of course, but it tells you that there's something wrong, seriously wrong with shadows. So you shouldn't trust it. That's the idea. And yeah, I can show more examples like this one, okay, people hiking, and you can see that also in this case, if you have some shadows, you can do the same kind of analysis. And with reflections, you can do the same. You just click on an object on the mirror, and then you select the range of points that could be responsible for it here, okay, or vice versa. And you see that in this case, these do not intersect, okay. This is another nice example, okay, where I connected points on the mirror to objects. And although it's not very trivial to say whether the reflection is right or not by the naked eye, through this analysis, you can see that the system is unfeasible. It's written in red down here, okay, meaning that there's something wrong. Finally, one more way you can use is detecting inconsistencies in perspective, okay? So what does this mean? Let me show you. So here we have an image, okay, of a kitchen created with, I think it was Dali. I think I can use my filter to know it. No, it was Midjourney, okay. So I created this image, and now clicked on the wrong one. I annotated the image like in this way. I connected with these lines using the visual inspection filter and my annotation feature, okay. I connected the vanishing lines for several directions. So the red lines are these from the tables because I know they are parallel. This is a square table, okay. And they intersect in this red point here. Then I do the same for this other table here, and they do intersect in this yellow point. And then the same for this direction, and they do intersect in the green point. Until now, everything is very good. So you can see that Midjourney did a very nice job because we do expect these lines to all lie on the same horizon, which is this purple line, you can see. And we have indeed a good alignment. Okay, so the perspective is very nice. But unfortunately, the moment we go and take the tiles on the floor, okay, you connect them and they meet here. This is wrong. They should meet on the purple line as well because everything here is parallel. The floor and the tables, okay, are parallel to each other. And so the orange point, if the image was original, trustable, true, should have been on the purple line, on the magenta line, sorry. Yeah. So this is also a way you can use. Okay, perfect. That said, we have seen several ways you can use, but the best way to go is always a combined analysis when possible. So instead of trusting just one way, the best thing you can do is to build together your analysis, combining together different approaches. Like in this example, I have this picture of me with one other person, okay? If I go and check the file format, you see that, yeah, in the metadata we have GIMP as the editing app, while the original make and model are my Google Pixel 3a, okay? So you see that Authenticate is already raising a warning for you. Look, EXIF software is an editing application, and also the EXIF create date is different than the modify date. You can see that there are months of distance between the two, okay? So this is suspicious. Then I go and I check with aligned double JPEG, the JPEG filter, and I found this map. So this is probably suggesting me that we have something wrong with this face, right? The output is quite clear. But what happened to this face? I go and use face gun, and I find that this image is detected as a gun. And now I can build up a convincing story, you can see, because I could say, look, the image seems to be compatible with a Google Pixel 3a, okay? But there are traces of manipulation in this face. And we have reasons to believe that they taken an image with a gun, they scaled them to make it fit here, okay? And they probably also adjusted the skin tone of the neck to make it match to the one of the image, okay? And placed it here, okay? So if you build up a case like this, and that's the true power of Authenticate, because you can create projects, bookmarks, comment on bookmarks, and create a compelling report, that's the best way to deliver a convincing result. Okay, we have a few minutes left, so let's go to the final conclusion. Okay, sorry. I forgot to mention the behavioral and physiological methods. These are even more advanced, I would say. They discovered that, for example, for video deepfakes, you may have inconsistencies in the eye blinking frequency. Like they found that in some deepfakes, people never blinked their eyes, okay, which was strange. Or that when you are plugging a face into someone else's face with a deepfake method, the direction of the entire head is not always consistent with the direction you computed if you consider only the central part of the face, because you will only change the central part of the face, not the entire head, okay? And so if you have this discrepancy, that means something. Then you can compare the movement of the mouth with the audio, and if the mouth, the way the mouth moves is not compatible, consistent with what it's saying, this is also suspicious. You can find all papers about this at the bottom here. And then even more advanced stuff, okay? So I will just skip it now. So final remarks, are deepfakes a potential threat? Well, yes, okay. As every technology, it can be used for the good and for the bad. We could use deepfake technology to dub the movies, for example, automatically and save a lot of money. But we can use them as a weapon to do misinformation, non-consensual pornography, and so on and so forth. So what can we do to combat the weaponization? Of course, we will work on detection method. That's our job, to provide you with more and more powerful and diverse detection methods. We have to hope that the social networks will implement some policies, okay, to combat the diffusion of deepfakes. So as soon as something is detected as suspicious, it's blocked and not shared around. And we have to educate people that unfortunately nowadays seeing is no longer believing, right? Okay, I think that's all. Here I have some recommended readings if you want to learn more about this, okay? And if you have questions, I'll be happy to answer. Now I will answer the question that I have here, but if you have more, you can write to my email address. It's here, and I will answer as soon as I can. So thank you. I will now go to the Q&A box. Okay, perfect. Okay, there is this question: which models are used by adversaries in generating deepfakes? And does the model used affect the analyst's ability to detect it? So I will first answer the second question. Yes, of course, because if a very popular model like, I don't know, DALL-E, okay, or Midjourney is used, it's easier for the detector and for the people developing the tool like us to train on it because it's widely available. We can use APIs to create images. While if the attacker uses an homemade customized model and they tweak it with the settings a lot, it will become more difficult for us because it will be more divergent from the training set. Unfortunately, we don't know which model are used by adversaries. So this is one of the things we are trying to discover. Okay. And unfortunately, there are models that are specifically trained on illegal images, so as to say. So it's an open battle. Yeah. I think we can go to the next one. Google Pixel 9 can use AI at the camera level. How could we check to see if the photo has been manipulated directly from the device? And this is a very good question. Thank you for asking, because this is a raising concern. We are actually trying to create a European research project about this, because indeed it's an issue when AI enters the acquisition pipeline, and it is doing, it's happening, okay? Some producer of imaging sensors are embedding AI into the imaging sensors, okay? So the image is AI processed even before it exits the sensor. It's an open question. There are some papers published recently where the researcher proposed to create trustability map that should be created by the smartphone itself that would tell you, look, this and this region of the image has been enhanced with AI, while these and these are true to the original scene, okay? The real answer is we don't know yet. Also because, of course, Google is not willing to give you their algorithm because, of course, they spent billions on it, okay? So we have to wait to have enough material and study it. That's the idea. But trust that there are thousands of researchers working on this. So Amped Authenticate uses full data-driven deep learning approach to understand if an image video has been generated using any of the 3 deepfake models. Is this understanding correct? Oh, yes. So if you go on our blog, there is an article about what we use in our algorithms, so you can have a better understanding, okay? But yes, basically, yes, we use full data-driven. The model we use for the diffusion model filter is based on a recent scientific paper that uses CLIP, which is a famous feature extractor, and then uses a support vector machine classifier on top on it to classify images. So it's a combination of 2 machine learning methods to reach the classification. Next, please. Could you show the amped confidence number for the image of the boys in the park? Yes. Yes, it's this one, I think. Okay. Boys in the park, maybe it was the reflections park. This one. Or it was this one, I think. Sorry, I'm not sharing authenticate. Beg your pardon. I think it was this one. Okay. Can we see the next question, please? If there are more. Yes. What could be the advantages of deepfake? Well, I think you mean the good uses of it. Well, for example, in Hollywood, and not to replace actors, but if you have to translate movies to a different language, it could be much more convincing if you can change the movement of the mouth to the proper language. I can tell you because in Italy we have a lot of dubbed movies, and nowadays you can still see clearly, right, that although our people are very good in doing it, but the movement of the mouth is not consistent with the sound. if you can fix the mouth for this, you can make the movie better, for example. Or people working in marketing, they can create a lot of material without privacy concerns because they can create faces that do not belong to any people, and so they can use it without legal issues, for example. Okay, I think you will be able to access again the webinar, so you can see the slides through it without any problem. What degree of automation does the platform offer for video analysis? That's a good question. You have seen that we have dealt mostly with images now because we are still working to video deepfake detection. Okay, once this will be in, we have a dedicated module for videos, authenticated video. Okay, with a GUI entirely dedicated to videos. Once this will be available, you will be able to automate it because, of course, you get these scores, so they can be computed in an automated way. But Authenticate is mainly a tool conceived for the analyst. Okay, it's not a tool engineered to be used as a background tool that does everything automatically. It's something that, as you have seen probably from the interface, expects you to know what you're doing, basically. That's the idea. Is Amped working on autoencoder detection filter? Not at the moment. No, it would be interesting to detect images compressed with this kind of autoencoder. But if you mean video deepfake, because that's what's used for, yes, we are working on that. Okay, so we are working to do video deepfake detection, which is normally done with the use of an autoencoder. Okay, this is a very good question. I will not read it because it's very long, but you can all see it. No, there is no an established methodology within Amped software to accomplish this. The question relates to this method. Switch. I don't know if you're seeing my screen or not. Yes, okay, but I have to switch to PowerPoint. So the method is this one that you see here, okay? And the paper is this one, exposing deepfakes using consistent ad poses. So the issue here is that researchers publish a lot of stuff, okay, very interesting. But when a company has to implement this and make it available to the public, you have to consider whether it is practically feasible to implement these systems, okay? Because they maybe work very well in the lab, but then creating an interface and making it work in the wild is not as easy. So that's why we will never be able to implement everything you find out there. That doesn't mean you could probably find the code of their method on the website of the author, and you could try it. Okay. I think we are done. I don't see any other question here, so we'll go back to my final slide with my email address. And we are also running out of time, so unless you have more questions, no, I don't see any other question coming. So I would like to thank you a lot for being here today with me. I hope this was useful information for you. And once again, if you have comments, feedback of any kind or questions, please write to this email address and I'll be happy to answer. Thanks a lot again, everyone, and have a nice day.